Very good morning, students.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, all of you. So let us start with the discussion without wasting any time. Okay, last class, this was the question which I have given as a homework. So what was the answer for this? Compare acidic strength R S double bond O, S double bond OH, R C double bond OH, C double bond OH OH, and phenol. Sulfonic acid, carboxylic acid, carbonic acid, and phenol. So if I have to compare acidic strength of any compound, I have to look at the stability of respect to conjugate base. That is what our discussion. Because acid is going to be H plus ions, along with the H plus ions, conjugate base is obtained or not? Acid is going to produce the H plus ion, along with the H plus ion, conjugate base is obtained. If the conjugate base is more stable, then I can say the dissociation of that particular acid into H plus and conjugate base will be happening at a greater rate. That means the acid is going to be a stronger acid. So try to write the respective conjugate bases for all the acids. So you will be having R S double bond O, S double bond O minus. Here you will be having R C double bond O minus. Here you will be having C double bond OH and OH is there, right? H2CO3, C double bond O minus OH. If I just cleave one OH bond, and here I am getting phenoxide ion O minus. You try to compare the stability: sulfonic acid, carboxylic acid, carbonic acid, and phenol. Can I say sulfonic acid is having the respective conjugate base of R S double bond O minus? If I try to write the respective resonating structures, I am getting three equivalent resonating structure, and out of these three equivalent resonating structure, in all those structures you will be having negative charge on more electronegative oxygen atom. Because of that, it is going to be highly stabilized. Carboxylic acid has two equivalent resonating structure. Carbonic acid, if I try to cleave this OH bond also, I'll be generating C double bond O minus, which is again having good resonating structures or not? Yes or no? And D, you have phenol, where the phenoxide ion is stabilized by just normal resonance. So A greater than, B greater than, C greater than D, that will be the right order. So you can say sulfonic acid gives sulfonate ion which has three equivalent resonating structure. Carboxylic acid gives carboxylate ion which has two equivalent resonating structure. Carbonic acid has bicarbonate ion, here where OH, only one OH bond is cleaved. If you try to cleave the other OH bond, you will be getting C double bond O minus, which is nothing but your carbonate ion, which has quality resonance. That means the negative charge comes into pi electron and moves away. If you include the lone pair of electrons and oxygen into resonance, in all the resonating structures you have negative charge on more electronegative atom. And phenol has just phenoxide ion which has resonance stabilized. Phenoxide ion has normal resonance. So A greater than, B greater than, C greater than D, that is the correct order of acidic strength. Is that clear to everyone?
Yes.
And is my
Yes,
voice
sir.
clear to all of you?
Yes, sir.
Yes, sir.
Yes. Shima, just check your internet connectivity. If myself has an issue, that should be, every student should have the problem, okay? Please check your internet connectivity and join again. So then let us continue with the next example. Compare acidic strength: formic acid, benzoic acid, acetic acid, HC double bond OH, PHC double bond OH, CHC double bond OH. Try to give the answer. HC double bond OH, PHC double bond OH, CHC double bond OH. Look at the general case like C double bond OH group connected to some any alkyl group, any group G. C double bond OH will be giving what? G C double bond O minus. This is some group G and H plus is obtained. Now I am looking at the respective carboxylate ion, and if you try to write the respective resonating structure or resonance hybrid of this carboxylate ion, you have C double bond O minus, COO. This is what the pi electron density moves, and that is what in resonance with the negative charge. The pi electron density, pi negative conjugation is there. If you look at the CO3, CO2 minus, that is carboxylate ion. In the carboxylate ion, we already have negative charge. That is already electron density is high. If this group G is electron donating group, In that case, if G is an electron donating group, electrons are giving to the carboxylate C double bond O minus, where already electrons or electron rich center is there. So whatever the electrons donated by this group, they are going to repel the C double bond O minus system or not. If G is a donating group, then it destabilizes or stabilizes. It destabilizes. And if G is electron withdrawing group, if G is electron withdrawing group, then it stabilizes. Destabilizes CO minus, it stabilizes COO minus. So understand these cases, students. G is an electron donating group connected to CO2 minus. If electron donating group is there, if G is donating the electrons, or where CO2 minus, that is C double bond O minus, already has negative charge. In that case, destabilization is going to happen. If this is unstable, then the acidic strength is going to be decreased. Now compare formic acid HC double bond O minus, it is a conjugate base given. Benzoic acid pH C double bond O minus, acetic acid CH3 C double bond O minus. CH3 is also donating the electrons by inductive effect. pH is also donating the electron by mesomeric effect. Which will donate greatly? The electron donation by phenyl group is great or CH3 is great? The electron donation by phenyl group will be great or CH3 will be great? Because CH3 is donating the electrons by just inductive effect, but the phenyl group is donating the electrons by mesomeric effect. Phenyl group will be having more electron donation, but with respect to just electron donation, you cannot say benzoic acid is going to be least acidic. Why? Because the electron donation is actually happening through resonance. Resonance stabilizes the system. Here in formic acid, there is no electron donation happening at all. So formic acid, what I can say, formic acid, no electron donating group. If there is no electron donating group, because of that, there is no destabilization happening. So formic acid is going to be having the lowest pKa. Lowest pKa means highest Ka. Ka will be high. Ka is highest. Ka is highest means most acidic. Formic acid is going to be the strongest acid. After formic acid, if you look at benzoic acid and acetic acid, benzoic acid is actually producing benzoate ion, which is actually resonance stabilized. That is why it will be more acidic. And acetic acid is going to be not having any resonance, just the methyl group is electron donating, which will repel the C double bond O minus system and making it unstable. So A greater than B greater than C, that will be the right order of acidic strength. Formic acid will be having the greatest acidic strength, then benzoic acid, then acetic acid. This order, how do we get? This order we got from the respective electron donating tendencies of these methyl groups and the phenyl group. Although phenyl is donating more electrons, but it is resonance stabilized. Because of that only B will be having greater acidic nature when compared to C. And A, no electron donating group, that's why it will be having the greatest acidic strength. Right? Acidic strength of phenol and substituted phenols. So obviously phenol is going to have respective, phenol is going to produce respective phenoxide ion. If the OH group is lost, that is if the OH group is cleaved, we will get negative charge on oxygen. This negative charge on oxygen will be coming into, yes or no? This negative charge on oxygen comes into, pi electron moves away. So we will get resonating structures where negative charge will be developed at ortho and para positions. That means phenoxide ion is actually, the O minus is actually electron donating through mesomeric effect. And if we have any groups which are electron withdrawing, the electron withdrawing groups remove the electron density, making the system stabilized. Electron donating groups will donate the electron density. Phenoxide already electron rich, and we are donating electron density. Because of that, repulsions will be high. Yes or no? So electron withdrawing groups, whichever are connected to the phenol, that will be more acidic when compared to no substitute phenol. And electron donating groups are least acidic when compared to normal phenol, just because of repulsions. Try to answer this. Compare acidic strength of phenol and substitute phenols. Give the answer, students. A, B, C, D, 4 compounds I have given to you. So GOC is all about solving different examples. We have studied all effects: inductive, mesomeric, and hyperconjugation. You can apply all these effects. Electromeric effect we'll study because that is a
is
not a.
A is greater than B, C, D.
So what was the answer? A
E is greater than
greater than
B,
B,
greater than C.
greater than C, greater than D.
Yes, sir.
OCH3. Just look at
Sir,
OCH3
D
book.
will C will be highly destabilized, sir,
Yes,
because
because OCH3 is electron donating group, right? NO2 minus M will be more. CHO is also having minus M. NO2 and CHO are minus M groups, but when you compare NO2 and CHO, minus M will be more for NO2 than when compared to CHO. OCH3 will have plus M because lone pair of electrons are present on oxygen which are donating electron density into the ring. So what is going to happen is OCH3 plus M and phenol, you don't have any substitution, no effect. No effect. So NO2, CHO are electron withdrawing and OCH3 is electron donation. So A will be having greater withdrawing. So A will be most acidic than B. After B, you will be having D, where you don't have any effect. After D, you will be having C, where you will be having least acidic nature because of electron donation tendency. Got it? Answer here. Compare acidic strength of phenol and substitute phenols. All of you answer here. Orthonitrophenol. Orthonitrophenol.
ACBD.
Metanit. ACBD. One answer. Anyone? Anyone else?
So D, C, A, B, sir.
DCAB. Anyone else?
C, A, D, B.
E A B D.
CADB or
D,
BD?
D, D.
B D, sir.
D.
Okay. So let us try to compare what is actually happening here. Orthonitrophenol, you will be having NO2 group same. So minus M, minus M, minus M. And if you look at NO2, NO2 is sorry, in B you do not have minus M, right? Because NO2 present at NO2 present at meta position cannot show mesomeric effect. It will show only inductive effect
Minus I, yes, sir.
minus I. But what happened with minus I? If you look at A and C, minus M is common. Minus I will be more in A, minus I more, minus I less. Why? Because of distance. But if you look carefully again, in A you have intramolecular hydrogen bonding or not? Generally, the expected order is minus M is same in A and C because A, B, C should be more acidic when compared to D because they are electron withdrawing. When which is withdrawing great electron density? It should be A generally because it has minus M and minus I more. But A has intramolecular hydrogen bonding also. Generally expected order is A should be greater than C, and after C you should have B, after B you should have D. But A and C order, if you look carefully, C will be greater than A, then B, then D. This will be right order because of intramolecular hydrogen bonding. CABD. Okay. So minus M effect, minus I effect, minus M, no effect. Expected order will be A should be greater than C, C should be greater than B, B should be greater than D. Due to intramolecular hydrogen bonding in orthonitrophenol, acidic strength decreases because of partial positively charged hydrogen developing attraction with partial negatively charged oxygen. The OH bond is not cleaved greatly, so you will be having CABD as the right order. Is that clear, students?
Yes,
Yes,
sir.
sir.
Yes, right. So now compare here. This is very simple. Compare acidic strength of phenol and substitute phenols.
CBA.
CBA because greater the number of,
CBA.
yes, very good all of you. So
Electron
greater the number of NO2 groups, greater the number of electron withdrawing groups, greater will be the stability of the respective conjugate base. So acidic strength will be C greater than B greater than A, right? Try to compare here. Orthocrystal, metacrystal, paracrystal.
ABCD.
ABCD. What
No,
are CH3
sir.
groups? What are
D,
CH3
C,
groups?
A, D. D, C, A, D, sir.
CH3 group is electron donating. Yes.
DCAB, DCBA.
CH3 is electron donating group. In a D, you don't have any electron donation tendency. But in A, B, and C, you have electron donation tendency, which is going to donate the electron density greatly.
D.
A,
Why? Why?
because of least distance.
Closer to.
Because we only have plus I effect.
No, they have hyperconjugation as well. So along with the inductive effect, we will be having hyperconjugation for methyl groups. Whenever we have substitution present at ortho and para positions, we will be having hyperconjugation also. I have told you about hyperconjugate effect, right? So they are plus H effects. Yes or no? So you will be having this group CH3 is present here. The CH electron density comes into the carbon-carbon pi electron density moves away. So this is how the resonating structure can be written for respect to hyperconjugative structure. Okay. So you have A and C will be having hyperconjugation, and A and C will be having hyperconjugation because substitution is at ortho and para position, but B you only have inductive effect, and in C you don't have any effect. So since there is no electron donating group in D, so that we will be having most acidic nature. So D will be most acidic. And after that, electron donation in B is only due inductive effect. So when compared to hyperconjugation, inductive is less priority. So lead donation is happening in B, so B will be greater. When you try to compare A and C, where the electron donation is greater, plus H effect is same, but also you can say plus I is more where, plus I is slightly more here, plus I is slightly less. Yes or no? So if you compare that order, A and C will be generally almost having almost same acidic strength, but if you try to compare in reality, C will be having lesser. Okay, so D greater than B greater than C greater than A. D greater than B greater than C greater than A. This is the correct order because plus I is slightly less in C, whereas plus I is also more in A. So D, B, C, A, this is the right order because of distance. After hyperconjugation, I am comparing the distance using the inductive effect. Arrange the following in the decreasing order. This question I have asked earlier. So CHCl3, CHF3.
C.
CCl3, CHCl3.
CHCl3 is more acidic because CCl3 minus is going to be resonance stabilized. P pi D pi resonance is going to be present. Yes or no? Upon loss of H plus, you will be forming CCl3 minus. Here it will be forming CF3 minus. This negative charge can come into resonance because in chlorine we have vacant 3D orbitals. Whereas in fluorine you don't have such resonance, so you have P pi D pi resonance in CCl3 minus. Because of that resonance, it is going to be more stabilized. So acidic strength, if you try to compare, A will be greater when compared to B. Right, students? Let us proceed further. Basic strength, like I'm applying all the effects now: inductive, mesomeric, hyperconjugation, every effect. Basic strength means what? Species which can share lone pair of electron to H plus. Basic strength is directly proportional to Kb, inversely proportional to pKb. So Kb higher means it is a stronger base. pKb lower means Kb will be higher, because pKb is equals to negative logarithm of Kb. And we have solved a lot of questions from ionic equilibrium with the different cases as well. Basic strength directly proportional to Kb, inversely proportional to pKb. Basic strength is directly proportional to stability of conjugate acid, because base is going to attack the H plus ion and to produce conjugate acid. If base is stronger, then the attack is greater. If the attack is greater, then I can say stability is high. If a stability of conjugate acid is high, then I can say base is a stronger base. Same as your logic, same logic you have applied in the acid. Acid gives H plus and it forms conjugate base. Conjugate base is more stable, means acid is a stronger acid. Similar to the base, if base is a stronger base, then the respective conjugate acid is going to be having higher stability. So stability of conjugate acid, that is again directly proportional to ability to donate electron. Generally, if you consider guanidine, amidine, and then lone pair localized and then lone pair delocalized. If you compare guanidine, here you have 3 NH2 groups where we have lone pair of electrons and 2 nitrogens, and this lone pair of electron, this nitrogen is localized. This will be having highest basic nature because of more number of nitrogen atoms and more presence of lone pair of electrons. Then amidine. After that, you will be having lone pair localized. Like if the lone pair is localized, if the lone pair is under delocalization, the net availability for the donation is less. Yes or no? Like if the lone pair of electrons and nitrogen is delocalized, then it is not freely available to donate or to attack the H plus ion. Yes or no? So that is, if you are rich, you can donate. If you are not rich, you cannot donate. Yes or no? If you are in debts, you cannot donate. So same thing, if you have more electron rich, that means if you are electron rich, obviously the donation is high. If you don't have the electron density, the donation is not accepted because not possible at all, first of all. Same thing, lone pair delocalized means delocalization involves the decrease in electron density on nitrogen atom. Because of decrease in the electron density, obviously the electron attack on the H plus ion is not possible. That is going to be least basic. So these are the basic logics. We will solve different examples. You'll get the idea. Compound which is most difficult to protonate, or you can just arrange them. A, B, C, D, 4 are being given to you. You arrange them in the increasing order of or decreasing order of basic strength. Which is most basic, which is least basic. A, B, C, D, 4 compounds have been given to you. So compare A. This aniline.
CBD.
C, B, D, A. Why, Faizan?
Because of plus I effect, it will donate electron.
Very good.
Then
In C, you have 2 methyl groups which are electron donating. In B, you have only 1 methyl group electron donating again. Whereas in A and D, you have lone pair of electrons and nitrogen involved in resonance. Yes or no? In A and D, you have lone pair of electrons or nitrogen involved in resonance. So more resonance, where it is available? In aniline, because of more number of resonating structures, because total pi electron density of the phenyl group is in resonance. So highest electron density in C, then B, then D, and then A. More delocalization of lone pair, CH3, less plus I, more plus I, maximum basic, less delocalization of lone pair. So you'll have C, B, G, A, that is the right order. Is that clear to everyone or not?
Yes.
yes, sir.
Yes, right. Try to compare here. This is also very simple. Compare basic strength PH3N, PH2NH, PHNH2, PHCH2NH2.
A, B, C, D.
Sure, Chima?
DCBA.
Because we have to look at the electron density of nitrogen, not the more resonating. Okay. If you look at a triphenylamine, the lone pair of electrons and nitrogen, they were in resonance with the 3 phenyl groups. If you look at lone pair of electrons and this nitrogen, they were in resonance with 2 phenyl groups. If you look at aniline, lone pair of electron is in resonance with only 1 phenyl. Whereas in benzylamine, there is no resonance, just the inductive effect of CH2 is activating. So in D, you have electron density increased on nitrogen, whereas in A, B, C, electron density of nitrogen has been decreased. Where it is decreased greatly? In C, it was decreased greatly. In A, it is decreased greatly. Why? Because of 3 phenyl group resonance. So after D, you will be having C. After C, you will have B. After B, you will have A. Okay, DCBA, delocalization of lone pair decreases. More is the resonance, more will be the delocalization. So more the relocalization, less will be the electron density available on nitrogen. If less electron density available on nitrogen, the attack will be less. So D greater than C, C greater than B, B greater than A, that is the right order. Clear now?
Yes, sir.
Yes. Try to compare here. CH3, CH2, NH2, CH3, CH double bond NH, CH3, C triple bond N. So what's the difference? So do we
ABC.
have resonance? Do we have
ABC.
resonance? You don't have resonance? Yes or no? So just the difference is the electronegativity of nitrogen. Why? Because in the difference in the hybridization of
ABC.
nitrogen atom. So if you look at compound A, in compound A we have nitrogen which is sp3 hybridized. In compound E you have nitrogen which is sp2 hybridized. In compound C you have nitrogen which is sp hybridized. This is for nitrogen, not for carbon. Okay, sp3 nitrogen is less electronegative, sp nitrogen is more electronegative. More electronegative atom can withhold the electron density. So lone pair on nitrogen in sp hybridized nitrogen is staying on nitrogen, the attack is not happening. Whereas on sp3 hybridized nitrogen, lone pair is not staying greatly, it can be attacking. So A greater than B greater than C, that will be the right order of your basic strength. Very good. Compare here A, B, C, D. You have to solve a lot of such examples to get a command over the subject. The same concepts we can even apply in different reactions. Like once you go with the GOC2, where I'll be discussing reactions, there we can again correlate the same concepts, because which reaction will be having greater rate for decarboxylation, for electrophilic substitution, for nucleophilic substitution on the aryl halides. All such cases you will have again the same correlation. Okay, anyways, try to compare basic strength here. A, B, C, D,
A, B,
four
D, C.
compound. A, B, D, C. A, B, D, C, right? Okay, one order. Anyone else? So what is the first compound A? In first compound A, there is no resonance, and you have just electron donation from two sides. So thereby increasing the electron density of nitrogen. And also nitrogen is sp3 hybridized. In second compound also, lone pair of electrons on nitrogen is localized, because it is already having 3 double bonds which were in resonance. So lone pair of electrons on nitrogen localized. And you have this nitrogen is sp2 nitrogen. So when compared to sp3 nitrogen, sp2 nitrogen is more electronegative. Greater the electronegativity, greater will be the tendency to withhold the electron density. So less will be the basic nature. So A should be greater when compared to B. And if you try to compare C and D, lone pair of electrons on nitrogen were under resonance, were under delocalization. So lone pair of electrons on nitrogen were under delocalization. And if you try to compare C, how did you say D greater than C, Faizan?
Because of less resonating structures in D.
In D we have less resonating structure. How can you say that? Have written all the resonating structure, 5 resonating structures. Like you have negative charge here, first point, then pi electron is coming here, negative charge here, then pi electron is coming here, negative charge will be here. Then pi electron is come here, negative charge can be here. 1, 2, 3, 4, and 5. 5 resonating structures are also possible. Yes or no? If you try
Yes,
to
sir.
look at compound D also, the respect to resonating structures are going to be in this fashion. Let us try to draw. So we have negative charge here, NH double bond, negative charge coming into pi electron density moving away. So now how to compare now? All of you think on comparison.
Sir, after donating, D will become anti-aromatic and C will be
Very good.
aromatic.
I have given the same example earlier also, right? Whenever I'm explaining the anti-aromatic nature, I have explained the compound D as well. Yes or no? D will actually become anti-aromatic in nature. Because of anti-aromatic nature, it will be highly unstable. Because of anti-aromatic nature, the compound D will be highly unstable. But it is not just due to resonance. Okay, that point you need to understand.
Yes, sir.
Yes. The question goes like this. So localized lone pair on sp3, localized lone pair on sp2, delocalized lone pair, delocalized lone pair. But after the attack, lone pair of electrons on nitrogen attacks H plus means it will form 4n plus 2 system, cyclic, complete conjugation, planarity is maintained. So D will be anti-aromatic nature, which is highly unstable. So this attack is not going to happen at all. So A greater than B greater than C greater than this is the right order of your respective basic nature. Right. Try to compare here. Compare basic strength. pH NH2, CH3, C double bond NH2. If you try to compare lone pair involved in quality resonance, so do not accept proton readily than yes or no. In B, lone pair involved in quality resonance. Why? Because if you try to draw the resonating structure of B, you will be having lone pair of electrons and nitrogen involved in the pi electron instead of C double bond O. So CH3 CO minus double bond NH2 with a positive charge on nitrogen. Negative charge on oxygen is more stable or not? And nitrogen is less electronegative atom. So because sp3 hybridized nitrogen. So lone pair of electrons and nitrogen, if you try to involve them in the resonance with the pi electron instead of C double bond O, you are getting negative charge on more electronegative atom. Because you are getting negative charge on more electronegative atom, that is highly stable. Whereas in compound you have aniline, where if you try to write the respective resonating structure, you have negative charge on carbon atom, which is less stable. Yes or no? So obviously, like net electron density, where we have high, net electron density is high on the nitrogen of A when compared to the nitrogen of B, because it is involving in the more stabilized resonating structure. So basic strength order will be A greater than B. Compare here, compare basic strength. Aniline connected with OCH3, CH3, NO2 and Cl. OCH3 electron donation, CH3 is electron donation, NO2 is electron withdrawing, Cl is also having net electron withdrawing. In OCH3, what is the effect we have? Plus M or minus M,
Plus M.
plus I or minus I?
Plus M.
Plus M. CH3, in compound B, what do we have?
Plus I.
Plus I or plus H?
Plus H.
You should not neglect this hyperconjugation. Okay, CH3, you should not neglect the hyperconjugation. NO2, minus
Minus
M.
M.
Cl,
Minus I.
minus I. So try to compare now, which are withdrawing the electron density greatly. NO2 withdraws the electron density greatly. Then chlorine withdraws the because minus M minus I withdrawing electron density, plus H and plus M donating the electron density. So A will be donating greatly, then B, and D will be withdrawing less, and then C. So A, B, D, C, can I say? A, B, D, C, because plus M effect of OCH3 is going to increase the electron density on nitrogen greatly. Then plus H effect of CH3 will also increase the electron density on nitrogen. But when you try to compare A and B, mesomeric is great, so A greater than B. C and D, NO2 is withdrawing the electron density greatly, so it decreases the electron density on nitrogen greatly. So C will be having less basic nature, because nitrogen electron density on nitrogen has been greatly reduced. In chlorine, you have minus I effect of chlorine is dominant when compared to plus M, so minus I have to take it. So A, B, D, C, the right order. Compare here. Compare CH3NH2, phenyl CH2NH2, aniline or the para substituted with OCH3, aniline metal substituted with OCH3. Look at A, B, C, and D. In A, in B, you have localized lone pair, and here you have plus I effect, and here you have minus I effect or not. In C, like although you say CH2 is electron donating group, but if you look at the CH2 group connected to phenyl, what happens is the pi electron density tries to withdraw the electron density. Like CH2, if it has positive charge, or the CH electron density, like if you try to write resonance in this fashion, the CH electron density comes into, pi electron density moves away. You get respect to resonating structure in this fashion. If you try to include the hyperconjugation with this particular double bond of alkene, if you try to include in this fashion, this electron density wants to come into the ring. That means this total group is going to be having a minus effect, that is electron withdrawing tendency when compared to electron donation. But it do have some plus I also, but effectively net dominating is minus I. OCH3 delocalized lone pair of electrons on nitrogen, and OCH3 is electron donating group plus M effect. OCH3 is at meta position, it will not have any resonance. It withdraws the electron density because oxygen is more electronegative. So delocalized lone pair and minus I effect. Yes or no? So try to compare. Now compare the order. Which should be more basic, which should be less basic. Can I say like this or not? Basic strength order A, B, C, D. Because in C and D, the delocalization of lone pair of electrons and nitrogen is there, whereas in A and B, there is no delocalization. In A and B, you have electron donation happening, like in A, in B, electron withdrawing happening just by inductive effect. But in C, electron donation is happening by mesomeric, but the net electron density of nitrogen is also in delocalization. So A, B, C, and D, that will be the right order of your basic strength. The next comes factor is steric inhibition of protonation. What do you, anyone know about the steric inhibition of protonation or SIP? Like it is generally for the ortho substitute amines. Ortho substitute aniline is less basic than its meta, para, and aniline. That is no substitute aniline due to steric inhibition of protonation. Like you take aniline, students. Protonation means what? Lone pair of electrons and nitrogen, they have to be attacking the H plus ion. So as soon as the lone pair of electrons and nitrogen attack the H plus, you will be getting a positive charge on nitrogen. Yes or no? You will be getting a positive charge on nitrogen because the electron density from nitrogen has been decreased. Nitrogen already has two NH bonds. Now the third bond is also going to be formed. So NH3 with the nitrogen having a positive charge, that is going to be your scenario. Right? Nitrogen will be having a positive charge and 3 NH bonds are there. Now, if we have a substitution at the ortho position, like let us not look at substitution as of now. Just look at respect to aniline ion. In this particular, like protonated aniline, what you will have positive charge is present on nitrogen atom. Because of positive charge on nitrogen atom, the NH electron density will be moving towards nitrogen or not? Yes or no? The
Yes, sir.
nitrogen has a positive charge, electron density present in NH bond, that will be moving slightly towards nitrogen because to neutralize that positive charge, because negative always attract positive. Because of that movement of electron density in the NH bond, this hydrogen develops partial positive, this hydrogen develops partial positive, this hydrogen also develops partial positive. Now, if you look at the partial positively charged hydrogen, they are surrounded by water molecules where you will be having partial negative on oxygen. You will be having partial negative on oxygen, where you will be having partial negative on oxygen, and water is having two OH bonds. That means, can I say the aniline ion is actually undergoing hydration or solvation? Yes or no? The stability of aniline ion is determined based on its respect to solvation also, because it develops a new intermolecular hydrogen bonding with the water molecules, or it is simply hydration, you can say. Now imagine the case wherever you have substitution at ortho position. If you have substitution or any group present at ortho position, this hydration will be decreased or increased?
Decreased.
Obviously, it has to decrease because the group G is going to repel the H2O molecules because of steric repulsions between this group G and the ammonium ion. The H2O molecules cannot come and develop intermolecular force of attraction, that is hydrogen bonding cannot be developed. So because of that, what happens? Solvation decreases. So ortho substitute aniline is less basic than its meta, para, and aniline due to steric inhibition of protonation. Why this steric inhibition of protonation is happening means because the respective aniline ion will be having steric repulsions with the group present at the ortho position. Because of that, solvation decreases. Because of that, stability of the conjugate acid decreases. Because of that, basic strength decreases. Right? So you can say respect to ortho substitute aniline is going to be less basic when compared to aniline, meta substitute aniline, and para substitute aniline. Reason is simple. So whenever we have aniline attacking H plus, you will form aniline ion, which is developing intermolecular force of attraction with water molecule, that is hydrogen bonding with water. But you have ortho substitute aniline. If you look at this particular ortho substitute aniline ion, it will have less solvation. So solvation decreases. Why? Because of steric repulsion. So stability of conjugate acid decreases, and basic strength, that will also be decreasing. Stability of conjugate acid, basic strength, solvation, all these three are going to be decreasing. So this is how the attack is happening. This is your ortho substitute aniline. So lone pair of electrons and nitrogen attack H plus. So we get a positive charge on nitrogen now. So the group G will repel the NH3 plus sterically, and because of that, this attack is not happening easily. Because of that, basic nature decreased. Is that clear with respect to the animation point of view also or not?
Yes, sir.
Yes.
Yes, right. Very simple, but you have to apply it carefully. So now compare basic strength: orthotoluene, metatoluene, paratoluene, and simple aniline.
BCDA.
Electron, yeah, electron donation is happening. Methyl groups are electron donating group, and obviously in every case nitrogen has lone pair of electron. Nitrogen's lone pair is delocalized. In A we can say SIR, SIP, steric inhibition of protonation. In a B and C, what do you have in B? Electron donation is happening by plus I effect. Here we have plus H effect. In a D, no effect. So where is the net electron donation high? In C it should be high because it has hyperconjugation. Then in B, and then in D, no effect, no electron donation. So C, B, D, and least is going to be A because of SIP. Yes or no? CBDA. So whenever you have methyl group, you should not forget the respect to hyperconjugation effect. That's what I'm repeatedly saying. Most of you are forgetting it. You should never forget, because if you just go with the inductive effect and distance dependent, then you should say B should be greater than C, which is wrong again, because in C we have hyperconjugation. In C, in a B, there is no hyperconjugation. Okay, C greater than B greater than D greater than A. A is going to be having least because SIP effect. C greater than B greater than D due to greater electron density on nitrogen in all the three cases. Compare here. In A we have SIP because ortho substituted aniline. In B, electron donate, NO2 is electron donating group or electron withdrawing group? Electron withdrawing. It withdraws the electron instead meta position by minus I effect. NO2 at para minus M effect. No effect. So can I say D will be having greatest electron density on nitrogen because there is no electron withdrawing group? Try to compare A, B, C, D. What is the right order now? A SIP, B minus I, C minus M, D is going to 0. A is going to be least because of SIP. Among B, C, D, D will be highest because no electron withdrawing group. Among B and C, which will be greatest? B will have more because of inductive effect only, whereas in C, electron donation, electron withdrawing is great due to resonance or mesomeric effect. So D, B, C, and least is going to be A because of SIP. Everyone got it? So least is going to be A because of SIP effect, steric inhibition of protonation. Try to compare here. Compare basic strength A and B. Try to compare basic strength here. Two compounds have been given to you, A and B. So which will have more basic strength? No one. Or two options, A greater than B or B greater than A. But you have to give the reason. A greater than B, why? Do you know SIR? SIR is steric inhibition of resonance. SIR indicates steric inhibition of resonance. We all say lone pair of electrons and nitrogen, they were in resonance with the pi electron density. This is going to happen only when this nitrogen and this phenyl group, they are in the same plane. But what happens because of two substitutions at the two ortho positions? Because of these two substitutions at two ortho positions, if this phenyl group was like this, the nitrogen which was present to be here, it moves away. So steric inhibition of resonance, because of that, this nitrogen is in different plane than phenyl group. The N connected with two methyls, that is in different plane when compared to phenyl substituted. So because of that lone pair of electrons and nitrogen, they were not in resonance. The resonance is not possible. Because of steric inhibition of resonance, you are not having the lone pair of electrons and nitrogen involved in resonance. So this nitrogen's lone pair is actually localized now. So delocalization of lone pair decreases due to SIR. So more availability of electron density in B. So B greater than A. So B will be greater than A, right? Because you may say that, sir, ortho substitute aniline or ortho substitute derivative of aniline. In that case, it should be least basic because of solvation decreased. But if you think carefully, the lone pair of electrons and nitrogen itself, they are not involved in the resonance because of substitution at both the ortho positions, right? That is why B greater than A. Then comes the concept steric inhibition of resonance, resonance SIR. If there is a bulky group at ortho position with respect to triangular bulky group in benzene ring, then due to steric hindrance, the triangular bulky group goes out of the plane, out of the benzene ring, and resonance between ring and group decreases drastically. Understand this. We have a benzene ring connected with two groups G1 and G2. What are the groups G1 and G2 can be? G1 is NO2, NR2, COH, etc. Only these three groups mainly. NO2, NR2, COH. NR2, the previous example is an NR2 group. Triangular bulky group. G1 is a triangular bulky group. Yes or no? So what are the triangular bulky groups? NR2, like NCH3, CH3 is triangular bulky group. If there is a bulky group at ortho position with respect to triangular bulky group in benzene, then due to steric hindrance, the triangular bulky group goes out of the plane. That means the phenyl ring and the G1 or the triangular bulky group which has lone pair of electron, they are not in the same plane. So delocalization of electron density, that is not happening, or that is decreased greatly. G2 is a bulky group. What are the bulky groups we can have? Methyl, ethyl, chlorine, bromine, iodine, NO2, NR2, COH. That means we can have both NO2 groups, both NR2 groups, both COH. In that case also you can say one is acting as a triangular bulky group, the other is acting as a substituent. G1 and G2 substituents you have to remember. And G cannot be what? G1 or G2 should not be fluorine or OH or NH2, CN or CH2 minus or CH2 plus. Whenever you have G1 or G2 like fluorine or OH or NH2 or CN or CH2 plus or CH2 minus, in that case SIR is not possible. SIR is not possible because of is not possible due to small size of these groups. Due to small size of these groups. Ortho effect. So then comes the ortho effect. Ortho substitute benzoic acids are stronger acids than benzoic acids and is also more acidic than its meta and para. Like you compare aniline. Ortho substitute aniline is a weaker aniline when compared to aniline, meta isomer and para isomer. Meta substitute and para substitute. Yes or no? If you talk of aniline, ortho substituted aniline is going to have less basic nature when compared to meta, para and no substituted aniline. When you compare benzoic acid, ortho substituted benzoic acids are more acidic when compared to no substituted, para substituted or meta substituted. This point you have to understand. This is your ortho substituted benzoic acid. It is most acidic when compared to no substituted benzoic acid, that is simple benzoic acid, or para substituted or meta substituted benzoic acid. The reason, what was the reason? SIR. What is SIR? Steric inhibition of resonance. So what do you mean by that? That means you have a phenyl group and where some substitution is present at ortho position and you have C double bond of OH. That C double bond OH will undergo the cleavage of OH bond to form respect to carboxylate ion C double bond of O minus. Can I say this is a bulky group or not? No, because respective you have this type of compound C double bond of OH will undergo loss of H plus ion, that is OH bond is going to be cleaved. Loss of H plus produce respective carboxylate and G group is present here. Think of the ortho substitute benzoate ion. This C double bond O minus is actually a triangular bulky group, and you have substitution at G. So ortho substitution group is going to repel, because if this G is a bulky group, because of the repulsion, the C double bond O minus, which should be in the plane of the phenyl ring, that goes out of the plane. That means if I have the benzene group like this, the C double bond which was present in this fashion, that will move away. We look at the animations, you will get the idea. If C double bond O minus goes out of the plane, that means the pi electron density of phenyl, earlier we can write the resonance in this fashion, that resonance you cannot write now. If you cannot write the resonance, what I can say? This phenyl group is actually electron donating group or not? Because you have R group connected with a C double bond O minus. This is a resonance hybrid. If this R group is electron donating, this benzene ring is actually electron donating by resonance. But if COO minus goes out of the plane, because it goes out of the plane, the phenyl group cannot donate the electron density by resonance. If resonance is not happening, one thing is electron donating is not happening to the COO minus. COO minus is already having electron rich, that is more negative charge is present. So if electron donation is not happening, it is stabilized or destabilized?
Stabilized.
Stabilized, right? Because it is CO minus is already electron rich, and you have electron donation from the phenyl group. If the electron donation from the phenyl group is stopped, the CO minus is not getting electron density, so that should be stabilized. Whereas in the meta or in the para or in the simple benzoate ion, you have donation or electron density from the phenyl group, that is in resonance. Whereas in the ortho substitute benzoate ion, there is no resonance possible with the respect to the phenyl group. Because of that, what we can say is, the ortho substitute benzoic acid, they are not getting the electron density. Since they are not getting the electron density, they are highly stabilized. Since they are stabilized, their acidic nature will be high. Okay. So let us look at animations as well. Respective benzoic acid, and you will be producing the respective benzoate ion like that. Ortho substituted benzoic, like you can look at the C double bond O minus and methyl group. They are out of the plane. You can look at simple benzoate ion where the C double bond O minus and phenyl group, they are in the plane. But whenever CH3 is present, the phenyl group and C double bond O, they are no more in the same plane. Yes, whenever we have this, look at now students, this phenyl ring is in perpendicular plane to that of C double bond O minus. Not exactly perpendicular, they are out of plane, you can say like that. Okay. C double bond O minus is in different plane. This pi electron density of the phenyl ring or the phenyl ring is in different plane. So because of that, what is going to happen? You will have more acidic nature. For the respect to ortho substitute benzoic acids. That is how it shifts. Okay, whenever we have a group substituted, look at this animation. Whenever we have the hydrogen replaced by the methyl group, because of the methyl group or any group, you have C double bond O minus which was in the plane, that is moving away. So pi electron density resonance is not possible. That is SIR. Compare here, compare acid strength. Ortho, meta, para, and no substitute benzoic acid. So ortho substitute benzoic acid, you should give ultimate order, like highest acidic strength. Yes.
Para.
What is the right order? A, B, C, D.
ACBD. ACB.
A, C, B, D. So let us look at that. So in A, we have ortho effect. In B, we have minus I effect because NO2 at meta position. In C, we have minus M because NO2 is at para. In D, we have no effect. Minus I, minus M, they are electron withdrawing. Yes or no? So A, C, B, D, ortho substitute will be having highest. NO2 and NO2 at meta will be having minus I, whereas at para it will have minus M. So minus M will be having great order. So after A, we have C. After C, we have B. After B, you have D. So A, C, B, D, that will be the right order of your acidic strength. Compare here, compare acidic strength. Chlorine can be one of the bulky group. Fluorine is not the bulky group. OH is not the bulky group. You have to look at that bulky group orders. G1 and G2 cannot be. What G1 and G2 cannot be? That point you need to know.
Chlorine, OH,
Chlorine.
No,
NH2.
G1 or G2 should not be FOH, NH2, CN, CH2 minus CH2 plus. Okay. So these groups will not have greater steric repulsions to make the plane differed. Okay. Those group will not have the effect to make the out of plane configuration or SIR effect. Chlorine is a bulky group, so it can repel the respect to COH. So ortho will be having greatest. Try to look at the other two cases. Yes or no? Chlorine will have minus I effect dominant. Minus I will be more because it is distance dependent again. Chlorine minus I. Chlorine here also minus I, because for chlorine when compared to plus M effect, inductive effect is dominant. So in the inductive effect, B will be having minus I more because it is at meta, because distance dependent. And in a compound C, you will be having minus I less, and in compound D no effect. So what you can say, A, B, C, D, this will be the right order, because more electron withdrawing is happening in compound B when compared to C because of minus I effect. Got it or not, students?
Yes, sir.
Yes. Try to compare here. A, B, C, D. The highest will be A because ortho substitution. The least will be D because no electron donating group. But B and C we have electron donating group. So which will have greater?
B.
Why? I have repeatedly said the same thing to you. Yes or no? Electron donating groups, they are going to destabilize the system. So plus I will be there in B, whereas in C we have plus H. More is the electron donation happening in C. So C will be going to be least, not D. Yes or no? D will be the second acidic after A, because in D you have no electron donation groups, but in C, B and C, you have more electron donation happening with respect to C. Because of hyperconjugation in B, you have only plus I effect. So among B and C, more is the electron donation happening in C, so C is going to be the least, and then you will be having B, ADBC. Okay. So if you compare inductive effect only, then you should say plus I will be more in B, plus I will be less in C. In that case, you will get A, D, C and B, which is wrong. Because in C you have hyperconjugation, because methyl group shows the hyperconjugation effect because of the presence of sp3 carbon having alpha hydrogens. 4, compare here A and B.
B.
Why?
Because C2H5 is a more bulky
More
group.
bulky group, because C double bond O minus will be moving more out of the plane. That means electron, the delocalization of electron density or electron donation from the phenyl group to C double bond O minus in C2H5 will be least. Ortho effect increases from left to right due to more bulky group at other position. So more acidic strength will be for compound B and then for A. Right, students? These are the different reactions where you can actually understand the application of acidic strength, basic strength, ortho effect, SIP, SIR, yes or no? All the effects we have studied with a lot of examples. You try to solve these examples many times. You itself will get clarity. Next concept is feasibility of acid-base reaction. An acid-base reaction will be feasible if it goes from strong acid to weak acid. That means if you have phenol treated with NaOH, the phenol can react with NaOH to form respective sodium phenoxides. Acetylene can also react with NaOH to form CH triple bond C minus Na plus H2O. So what we can say is reaction with NaOH is feasible if acidic strength, if strength of the acid, like acid is reacting with NaOH. We have 3 comparisons. We have sodium, NaOH and NaHCO3. So most acidic, okay, sodium is going to be more basic. It is moderately basic. NaOH is a strong base, we all say, but it is less weak base when compared to active metal like sodium. So So it all depends, strong and weak, that depends upon the opponent, right? NaHCO3 is going to be weak base. So weak acid, very weak acids can also be reacted with sodium. Comparatively strong acid, okay, or weak acid can also react with NaOH. Strong acid can only react with NaHCO3. Understand this point carefully. We'll be studying three reactions where the reaction with Na, active metal, metals are highly basic because of free electrons. NaOH, strong base when compared to NaHCO3, weak base when compared to Na. So if a reaction is happening with NaOH, we can say the acid should be more acidic when compared to water. You take alcohols, ROH, you take water, H2O. Water gives H plus and OH minus ion. Alcohol gives H plus and OR minus ion. Which is more stable among OR minus and OH minus? OR minus and OH.
OR minus.
Oh,
OR minus is more stable or OH minus is more stable? OR minus, you can say oxygen has negative charge and alkyl group is there. Alkyl group is electron donating group, which will be destabilizing or not? OH minus, there is no such alkyl group connected. In OR minus, you have a alkyl group, electron donating group is there. The electron donating group will donate the electron instead towards oxygen, which will make the OR minus unstable. Because of that, alcohol is a weaker acid when compared to water. ROH is a weaker acid than H2O. Understood this point, everyone? You have to apply the
Yes.
inductive effect of alkyl group when the acidic nature I am talking about. But when I am talking about OR group as plus I effect or plus M effect, in that case, you have to compare OH or OR, which is more electron donating. Which oxygen is more electronegative?
OR.
The oxygen in OR is more electronegative because of bond angle concept. Bond angle increases the electronegativity, which increases the percentage of S character. This oxygen is more electronegative. Since this oxygen is more electronegative, it cannot be donating its lone pair easily. Whereas this oxygen being less electronegative, it can use its lone pair in the resonance easily. So whenever you're talking about a basic acidic nature of alcohol and water, you have to look at electron donating tendency of alkyl group. Whenever you are connecting phenyl group with OH or phenyl group with OR, then you have to look at respect to electron donation based on the bond angle concepts. Oxygen in OR is more electronegative, so it cannot donate the lone pair easily. So ultimately, what you can say is water is a stronger acid when compared to alcohol. That means reaction with NaOH is feasible if acidic strength is more than water. So alcohols will not react with NaOH. That is alcohols, that is ROH, will not react with NaOH, but they do react with Na, active metals. CH3COH plus NaHCO3 gives rise to HCO3 plus CH3CO minus Na plus. That means the next comes a scenario, reaction with NaHCO3, reaction with NaOH is feasible. Earlier we have said reaction with NaOH is feasible when the acidic strength is greater than the water. Reaction with NaHCO3, NaHCO3 is still weaker base, so acid should be even stronger acid. So the acid should be stronger than H2CO3. Reaction with NaHCO3 is possible only when the whatever the acid you are considering, that should be more acidic when compared to H2CO3. Reaction with NaHCO3 is feasible if acidic strength of acid is more than H2CO3. Carbon of CO2 comes from NaHCO3. Carbon of CO2, here whatever H2CO3 gives H2O plus CO2, that carbon comes from NaHCO3. Acids which are more acidic than H2CO3 are soluble in aqueous NaHCO3 due to salt formation. Then you may ask a question, sir, how do we know? How do we know a particular acid is more acidic than H2CO3 or less acidic than H2CO3? The acidic strength you have compared, no? If acid is giving the respect to conjugate base, you compare the stability of the conjugate base. Based on the stability of conjugate base, you can compare whether that particular acid is more acidic than H2CO3 or less acidic than H2CO3. From that only you will be getting the idea whether that particular acid is going to react with NaHCO3 or not. Right? Which of the following is not soluble in sodium hydrogen carbonate, NaHCO3. For a compound to be soluble in NaHCO3, for an acid to be soluble in NaHCO3, it should be more acidic. It should be more acidic than H2CO3. That means H2CO3 gives what? H plus ion and HCO3 minus, OH C double bond O minus. This is the respective conjugate base. So you write the conjugate base in A, B, C, and D and look at which conjugate base is weaker than this or less stable than this OH C double bond O minus. You know, write the conjugate base here. First compound, if you write the conjugate base, you have NO2 groups at ortho and para positions, all the ortho and para positions, and you have O minus obtained here. Write the conjugate base here. Yes or no? O minus C double bond O. I can write this as enol or not? One OH group I can write as enol. This is enol, C double bond C OH is. I can write this as C double bond O. C double bond O. Can I write like that or not? This enol I am writing at keto form, and that OH group I have cleaved the OH bond to form respective O minus. That is the conjugate base. Here what will the conjugate base? C double bond O minus. Here what is the conjugate base? Phenoxide ion. So now we have to compare which of the following is not soluble in NaHCO3. That means the acid which is weaker than H2CO3, that is not soluble, that won't react with NaHCO3. Which is a weaker acid than H2CO3? How to compare that? H2CO3 gives H plus and HCO3 minus. So this is the conjugate base. If the conjugate base of these scenarios, if that is having less stability than HCO3 minus, then that is going to be weak acidic. You compare the conjugate base in A. The conjugate base in A is highly stabilized because of the presence of 3 NO2 groups at the ortho and para positions, because more electron withdrawing groups are there. Look at the conjugate, look at the respective conjugate base in compound B. The O minus comes into, yes or no? The O minus comes into, pi electron density moves away, and you can say more resonance is there in a compound B as well, because if you write the respective enol form, you will be getting this scenario. And if you try to look at this, all these C double bond groups, those C double bond groups are electron withdrawing groups, like pi electron density moves away towards oxygen. This is also going to be highly acidic in nature, squaric acid. Benzoic acids, they are highly acidic. Benzoic acids are highly acidic because the C double bond O minus is in resonance with the respective phenyl group. Phenoxide ion is just having normal resonance. Phenoxide ion is just having normal resonance. It is not having any electron withdrawing groups at ortho and para positions. So I can say compound A, B, C, they are more acidic because the respective conjugate bases are more stable when compared to HCO3 minus. Whereas compound D is less acidic when compared to H2CO3 because the respective conjugate base is not stable when compared to HCO3 minus. So with respect to that, we can say phenol is less acidic. That is Ka of H2CO3 is greater when compared to phenol. So we can say directly answer is D. I am not asking you to remember the Ka values. No one can do that. Yes or no? We have to compare the respective stabilities of conjugate bases and decide. Is that clear, students?
Yes.
Yes, right. Can phenol and benzoic acid be distinguished using sodium bicarbonate? Phenol and benzoic acid by NaHCO3?
Yes, sir.
Yes or no?
Yes.
Yes, because phenol is not more acidic when compared to H2CO3, but benzoic acid is more acidic than H2CO3. So benzoic acid can react with NaHCO3 to form a salt, whereas phenol cannot react. Yes, because Ka order is benzoic acid greater than H2CO3, and that is H2CO3 greater than phenol. And then comes the feasibility. Alkyne, whenever treated with the NaNH2, it forms ammonia plus the HC triple bond C minus Na plus. HC triple bond C minus Na plus. Reaction with NaNH2 is feasible if acidic strength of acid is more than NH3. NH3 is a very weak acid. NH3 gives H plus and NH2 minus. very weak acid. So NH2 minus is going to be a strong base, very strong base. So with the NaNH2, the reaction is going to be feasible when the acid is a stronger acid than ammonia. Look at these cases. Amines, ammonia, and those compounds which are more acidic than ammonia can produce hydrogen gas on treatment with sodium or NaNH2. Sodium is also active metal. NaNH2 is also very strong base. So NH3 upon reacting with Na, it forms NaNH2 and half H2 is released. Phenol can react with NaOH also. So phenol can also react with active metal like sodium because it is a very strong base. Active metals like sodium or aluminum are very strong bases as they have free electrons. CH triple bond CH plus Na gives rise to CH triple bond C minus Na plus half H2. H2 gas is going to be released. How is that happening? You can ask a question. So ammonia gives H plus ion and NH2 minus. And you have Na which is giving Na plus and electron. The Na plus is now going to be reacting with NH2 minus. Na plus and NH2 minus will react with each other to form NaNH2. H plus will take an electron. H plus will take an electron to form hydrogen atom. Two hydrogen atoms will combine with each other to form H2 gas. So H plus electron gives rise to half mole of H2. So this is how your hydrogen gas is evolved. From the evolution of hydrogen gas, we can also compare based on the quantity of H2 gas evolved. We can also say, we can also do some reactions like we can do some problems based on electrochemistry. Faraday's law I can apply. Like 1 mole of electrons is giving half mole of H2. 1 mole of electron will possess how much charge? 1 mole of electron is giving half mole of H2 gas. 1 mole of electron is equivalent to, what is the charge possessed by 1 mole of electron? Or what is the charge of possessed by 1 electron?
1.6 into 10 raised to our minus 19 coulombs.
So 1 mole of electron means you have Avogadro number of electrons. So multiply that with Avogadro number. So how much you will get charge?
9.6.
96,500 approximately, which is nothing but 1 Faraday. So charge possessed by 1 mole of electron is equivalent to, from this reaction, what I can say? 1 mole of electrons is equivalent to half mole of H2. Half mole of H2. That means 1 Faraday, 96,500 coulombs is equivalent to half mole of H2. At STP, 1 mole of H2 will contain 22.4 liter. So half into 22.4 liters at STP. So at STP, what I can say, if I pass 96,500 coulombs of charge, then I'll be producing half of 22.4 liters of H2 gas. That means 11.2 liters of H2 gas is evolved. So now I'll say a question like 10 amperes current is passed for 10 seconds. If a current of 10 amps is passed for 10 seconds, then what is the charge passed? Q is equals to I into T. So 10 amperes into 10, that is 100 coulombs. So if 96,500 coulombs is giving 11.2 liters, 11.2 liters of H2, if I pass a current of 10 amperes for 10 seconds, that means 100 coulombs of charge will produce. Therefore, 100 coulombs will produce 100 into 11.2 divided by 96,500. That many liters of H2. Like that, we can frame questions from the electrochemistry as well. Is that clear?
Yes.
Okay, whenever we have reactions which are producing gases like H plus electron gives us to half mole of H2. If I are doing that in the electrochemical cell, like electrolytic cell, then I can apply the equivalency condition and solve the different. Like I can say these many liters of H2 is obtained if a current of 10 amperes is passed for some x seconds. What is x? Like that also different questions can be framed. And if you look at this particular compound, cyclopentadiene plus Na, that is going to react with sodium to form respective cyclopentadienyl anion plus half mole of H2 is released. Why it is formed? Why this reaction is feasible? this reaction is feasible because this compound cyclopentadienyl anion is aromatic in nature. Yes or no? Cyclopentadiene, whenever it reacts with sodium, it forms cyclopentadienyl anion. Like whatever the CH bond present here, that bond can be broken and you'll get negative charge here. So that will be following 4n+2 Huckel's rule. Complete plenarity is there and complete conjugation and cyclic structure. So it is aromatic in nature. Because of aromatic nature, it is stabilized. Because of its stabilized, it will react with the strong base like Na and releases the H2 gas. Like which of the following compounds will release H2 gas upon reacting with a base like Na means you can just try to figure out those compounds based on their acidic natures. Right, students? Let us look at next concept. Like in which of the following cases reaction is feasible? CH triple bond CH. You try to answer this question. CH triple bond CH will react with only NaNH2. It cannot react with NaHCO3. It cannot react with NaOH. For a compound to react with NaOH, the acid should be more acidic than water. For a compound to be reactive with NaHCO3, the compound should be more acidic than H2CO3. For a compound to react with NaNH2, the compound should be more acidic than NH3. So CH triple bond CH is more acidic than NH3 or less acidic than NH3. NH3 is giving H plus and NH2 minus. CH triple bond CH is giving H plus and CH triple bond C minus. To compare, this is sp hybridized carbon. sp hybridized carbon will have electronegativity of 3.25. So sp hybridized carbon possessing negative charge is more stable. But here it is sp3 hybridized nitrogen will have electronegativity of just 3. So negative charge on CH triple bond C minus, this is more stable. So this conjugate base is more stable means this is going to be more acidic. So CH triple bond CH acetylene is more acidic when compared to ammonia. So it will react with NaNH2. Alcohols are weak acidic when compared to water. So they cannot react with NaOH, NaHCO3. So only NaNH2 they can react. PHOH phenols can react with NaOH and NaNH2. Carboxylic acid, benzoic acid can react with all the three, NaOH, NaHCO3 and NaNH2 is a very strong base. It can react with all types of acids. NaOH is a comparatively strong base. It can only react with those acids which are more acidic than water. So which are more acidic than water? Phenol, benzoic acid and substituted phenol. Yes or not the substituted? Ortho and para substituted phenols. All these are more acidic. And you look at NaHCO3. With NaHCO3 only benzoic acid and 2,4,6 trinitrophenol. They are going to be reacting because NaHCO3 is going to be weak base. So it can react with only very strong acids. Is that clear, students?
Yes, sir.
Yes, right. Then comes the next concept known as electromeric effect. What is electromeric effect? It is a temporary effect. It is not a permanent effect. This effect is going to be present whenever we have a reactive species. Generally, alkenes show this kind of effect. This is a temporary effect. The organic compounds having a multiple bond or a double bond or triple bond shows this effect in the presence of attacking reagent only. It is defined as complete transfer of shared pair of pi electrons to one of the atoms joined by a multiple bond on the demand of attacking reagents. Like pi electron in C is given to one of the carbon atom which were involved in the carbon-carbon double bond. It is divided into two types: positive electromeric effect and negative electromeric effect. In the positive electromeric, what happens is, in this effect, the pi electrons of a multiple bond are transferred to that atom to which reagent gets attached. Understand this point carefully. So we have C double bond C. The carbon-carbon pi electron in C is attacking the H plus. That means, can I say this reaction as the carbon-carbon pi electron in C is moving towards this carbon, and to that carbon attack is happening. That means the electron density move towards one atom and that atom is getting attached by a reagent. So the other atom gets positive charge. So this atom is connecting with hydrogen now. So attacking reagent is connected to that carbon to which the electron density has been moved to a. Yes or no? The C double bond C electron density moved towards an atom, moved towards the carbon atom, and that carbon is attacking the reagent. In that case, you will be having positive electromeric effect or plus C effect. We can also have another cases like C double bond C, any nucleophile. The nucleophile tries to attack this particular carbon, pi electron density moves away. So here what is happened, students? Here what happened in this scenario? We have carbon, carbon, and a nucleophile carbon form a new bond, whereas the other carbon has a positive charge. That means the nucleophile is connected to a carbon from which electron density moved away. So reagent is connected to that carbon from which electron density has moved away. So it is nothing but your negative electromeric effect. Understood this point or not? Positive electromeric effect means the electron density moved towards that carbon, where that carbon is now attached with the reagent. If the electron density moved towards one carbon and the reagent attacks the other carbon, then that is negative electromeric effect. In this effect, pi electrons of the multiple bond are transferred to that atom to which reagents get attached. Positive electromeric effect. Negative electromeric effect means in this effect, pi electron density of multiple bond are transferred to that atom to which attacking reagents do not get attached. For example, nucleophilic attack, like Cn minus attacking the carbon, this carbon, whereas pi electron density moved away to that, away from that carbon. Yes or no? Pi electron density moved away from that carbon, where Cn minus is actually attacking. It is nothing but electromeric. When inductive and electromeric effect operate in opposite directions, the electromeric effect is going to be predominant. The electromeric effect is going to be predominant where inductive effect and electromeric effect both have different, like both are in opposite. If both are opposing, then electromeric effect is going to be dominant effect. That is how you have to do the reactions, because the electromeric effect involves the pi electron density, which is involved in poor overlapping, whereas inductive effect involves in the sigma electron density, which is a stronger electron density. Is that clear or not? Everything so far?
Yes.
Yes. Yeah. And last point I have told you many times as well, so that we have left out tautomerism in the structural isomerism. Remembered or not?
Yes.
So that tautomerism we are going to discuss here, because we'll add the Bretz rule also here only. So what is tautomerism? When two structural isomers are in dynamic equilibrium with each other, they are known as tautomers, and this phenomenon is known as tautomerism. What actually it is? Tautomerism may be base catalyzed or acid catalyzed, and if you look at the analysis, look at this part. CH3 C double bond O. Okay, the reaction goes like this. CH3 C double bond O CH3 in the presence of OH minus, it forms CH2 double bond COH CH3. Yes or no? This is how the reaction can be understood. So how this attack is actually happening? Let us try to understand with the electronic effects or movement effects. C double bond O CH3 and CH3. Look at this C double bond O, the carbon double bond oxygen. The oxygen is more electronegative when compared to carbon. So can I say the pi electron density is moving towards oxygen? If the pi electron density is moving towards oxygen, oxygen develops partial negative, carbon develops partial positive charge. If carbon develops partial positive charge, what happened to the carbon-carbon electron density? That carbon-carbon electron density is moving. If carbon-carbon electron density is moving, this carbon is getting partial positive charge. Because of the partial positive charge on this carbon, this CH electron density again moves. Because of the movement of CH electron density toward this carbon, to neutralize that partial positive charge, a delta positive is developed on hydrogen. And we have a base OH minus. OH minus tries to pick up this proton. As soon as OH minus tries to pick up this proton, what happened to the CH electron density? The CH electron density is going to be donated to the next bond to form a pi bond. As soon as this pi bond is formed, this complete donation happens. So we will be having CH2 double bond C. C will have OH now. C will have O minus now, because pi electron density is given to oxygen. And here we have CH3. OH minus picks up the proton, so we'll have water now. We'll have water, loss of water obtained. So water is having two OH bonds. O minus tries to pick up this proton now, and ultimately will form CH2 double bond C OH CH3 with the release of OH minus. So OH minus is just a catalyst, base catalyst reaction. So in the presence of a base, the respective alpha hydrogens, whatever they are present, they are actually transferred now. So between these two products, you will be having an establishment of dynamic equilibrium. So whenever you have an alpha carbon should be sp3 hybridized, and alpha carbon should possess hydrogens. If the sp3 hybridized alpha carbon has hydrogens, those hydrogens can actually be shifting towards the adjacent C double bond O to form keto-enol tautomerism. Understood this point or not?
Yes.
Everyone got this point? So first question you should ask yourself, like if I take a structure like this, HC double bond O CH3, will it show tautomerism? Can I write this structure as HCOH double bond CH2? Because we have C double bond system. This is alpha carbon. On the alpha carbon, you have hydrogen. So this hydrogen can be taken away. This CH electron density comes into, oxygen picks up this proton. So HCOH double bond CH2. I can write like this or not?
Yes, sir.
Now try to understand the scenario. If I can try to write like this, that means I am moving the electron density of C double bond O. Let us understand the mechanistic approach clearly. HC double bond O CH3. I am moving this electron density, pi electron density movement, partial negative, partial positive. This electron density again partial positive. This electron density moved, you have partial positive here. So what I can say now? This CH electron density is actually coming into this complete movement happens because base OH minus picks up this proton. So we get HCO minus double bond CH2, and from water again the O minus picks up the proton to form HCOH double bond CH2. This is your keto form. This was your enol form, and OH minus is released back in the last step. Now understand this point. Why can't OH minus picks up this proton? Because we have the partial positive charge developed on this carbon. We have CH electron density present here along with the CC electron density. Why I am always looking for the carbon-carbon bond, alpha carbon possessing the hydrogen? Why can't the hydrogens directly connected to C double bond, those hydrogens be picked up? Why?
Sir, could you repeat the question?
The question is simple. The question is, we are actually making the carbon double bond is polar because pi electron density move towards oxygen. Because of that, we have delta positive charge here. Is that clear to you or not? Up to this point.
Yes, sir.
Now we have carbon-carbon electron density. Because this carbon has partial positive character, this electron density is moving. Because of that movement, this carbon also has some delta positive charge, inductive effect. Because of the partial positive on this carbon, the CH electron density moves. This is your alpha carbon. The hydrogen present on alpha carbon, that is slightly acidic, so OH minus picked up that proton. Now what I am saying is, why to look at a carbon-carbon single bond again CH bond? Instead of that, why can't the CH bond present, or why can't the hydrogen directly connected to carbon, that hydrogen be picked up? Why can't OH minus pick up this? Because the polarization is even more for this CH bond, right? Yes or no?
Yes,
When,
sir.
when compared to carbon-carbon single bond, then the carbon-hydrogen bond, the CH bond here is more polar. That is not happening because if CH electron density is picked up, this CH electron density has to be given to the next carbon, where you should have already pi electron density, repulsion will be high, and also due to steric repulsions. So H minus cannot pick up the proton from the carbon from that carbon which is already involved in C double bond O. It can only pick up from that carbon, from the alpha carbon which is sp3 hybridized, not from the same carbon. Got it or not?
Yes, sir.
And next question we should ask ourselves, what is the next question? If you are doing the reaction in the base catalyzed reaction, we are saying the OH minus can also act as a nucleophile which can attack this electrophilic carbon. Yes or no? Instead of taking OH minus as a base and trying and making the OH minus available or wait for the proton, OH minus can be also taken as a nucleophile, and it can attack the electrophilic center. That has to be controlled. because of steric repulsions again, OH minus cannot go and directly attack this particular carbon because there is a possibility of tautomerization. So we have to take OH minus, like OH minus base means you have to take OH minus in the alcoholic medium, that is preferentially acting as a base, not as a nucleophile. Okay. So there are three types of tautomerism: ketoenol. So CH3 C double bond O CH3 in the presence of OH minus, it forms CH3 COH double bond CH2. It is base catalyzed ketoenol tautomerism. Aldehydes and ketones having alpha hydrogens attached to sp3 hybridized alpha carbon shows this tautomerism. That is what we have explained. The details of other forms of tautomerism and where the enol form is more, where the keto form is more, what is bread stool. Tomorrow we'll cover up this and go with the next part of GOC, that is reactions. Different types of reactions are there, like addition reactions, elimination, substitutions. We'll discuss all those cases. Right, students? Thank you all, everyone. Bye.
Thank
And
you.
everyone thought of the question? Any answer for the question asked in last class?
No, sir.
So actually that was an interesting question. So what are the subatomic particles made of? Subatomic particles are not made of something which has mass. They are ultimately made up of energy. We are made of matter. That is, we are made of something which has mass. Molecules has mass. Atoms has mass. Atoms made of subatomic particles. Subatomic particles again have other particles like quarks, and they are also ultimately made of energy. So the matter is ultimately made of energy. So we are all energy fields. Okay, there is nothing called mass. Like you study in gravitation, right? Newtonian mechanics. What do you study in Newtonian mechanics? One body and the other body will have gravitational force of attraction. But what is a body? There's nothing called mass. There's all energy fields. Okay, so that's what I want to say. Fine. Thank you all.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.